My name is Tim Colton, and I'm a Senior Staff Applications Engineer at Silvaco. And today I'm going to be talking about Viso, or parasitic analysis and debugging. Okay, so let's talk about the problem statement. You know, as we dive down into the smaller nodes, down to from 65 to 3 or even further, the complexity of the designs goes up drastically, and that, along with that, also the parasitics go up drastically. What we're finding is that it's risking tape-out delays, and it's creating long iterations in post-layout simulations. And so what we're trying to do is, with this tool, is to actually explore the parasitics before it goes into simulation. To shorten some of these design cycles, we actually have a tool called Javaro. I'll be talking about that in a little bit, which actually does parasitic reduction. But that's only half the problem. The other problem is being able to identify things before you get into the lengthy simulations. Okay, so I wanted to introduce you to Viso. So what Viso does is you're able to, before you go into simulation, you're able to take the parasitic netlist, read it into Viso, and actually analyze the parasitics on the design. So that means that you're able to go in and poke around and go, okay, well, what's the point-to-point resistances of all my critical nets? I want to know that. Or what's the delays on these nets? What are the coupling capacitors that couple to these critical nets? And how is it used in the flow is in the typical design flow. We have a schematic layout, typical design flow. After layout, if you're doing pre-LBS extraction, not a lot of people do that, but if you do pre-LBS extraction, you can put that into Viso and do some sanity checking like opens, dangling net, but most people use it after extraction. The net list is fully cross-referenced with a schematic, and you can put that into Viso and say, okay, here's my list of critical nets. I want to go analyze point-to-point resistances on this group of nets. Give me a plot, show me graphically what this looks like, and then also give me a table and show me how it is sorted by delays, resistances, capacitances, and such. And then you can fix it in Viso before you get to simulation. Make sure it's like a kind of a scrubbing before you go into simulation, and by the time you get to simulation, it should be fairly known. Okay, here's a real-world example. In this particular example, we're doing it's a LVDS simulation, so low voltage differential signaling simulation. We're doing duty cycle optimization. So it's a duty cycle optimization type of simulation. So what they're looking for, an ideal thing is schematic, right? So we want about a 50% duty cycle. And that's ideal for this type of a design. And you can see in this design, we actually did extraction, and post-extraction ran simulation, and it ended up at 37%, so that's not quite enough. So we want to analyze where this problem might be without having to, again, go into the lengthy simulations. We've done a delay analysis this is a subsection of them, and we got the report, and it says, well, RxN1 and RxN2 have 17 picoseconds and 15 picoseconds respectively of delay. So those are the ones that are most likely causing me problems. And over here is a plot, and this isn't layout. This is actually the Viso GUI, and it takes the DSPF in and represents the layout in the Viso GUI. Can't overlay that on the GDS, and I'll get to that a little bit later. So now we can easily find which ones are the ones that are in violation, and now we're going to go one level down in detail and try and analyze what's really going on with these things to try and figure out what we need to fix in the layout. Okay, so we've analyzed these nets again. This is RxN1, RxN2. You can see from the thermal plot here, there's an area down here at the bottom that's red, and that's indicating, well, that's the highest delay on this net. And so that's an area of focus. So you want to go into that area, look at it, and if they go, oh, well, this is maybe on a metal 1, maybe I need to bump that up to a metal 3, 4, 5, which is a less resistive layer, or widen that wire and try and fix this problem. So we went into layout, we've done that fix, and then we did a new extraction, and now we can see waveforms are lining up, and our post-extract modified database is within specs. And so now we can go back into simulations and confirm that this is the case. Some of the other things that you can do, as I was talking about earlier, you can select one net, and so we've selected one pin up here at the top, and said, give me every single resistance, every path on this net, and show me the resistance of it, and then color them by, with a thermal plot. So the red ones are going to be higher resistance, and the green ones are less resistance. And then you can also get a chart or a graph over here of all of those nets that it analyzed, and you can sort them by delay over here in this column and be able to look at the net and get a better idea of where things might be wrong or might not, but at least you know what's in your design at that point. Another thing that's unique to our tool is you're able to actually do a layer contribution for a selected net. Like for instance here, it's this net valid. We're trying to figure out, okay, for delays, what is the contribution? Which layer contributes the most to the delay on this net? And so you can get a chart over here. Our metal 3 by far has the most contribution to the delay on this net. Metal 2's next, the vias next, and then metal 1 and other vias. So you're able to analyze everything again before simulating. Along with the resistances and delays, we can also do net-to-net coupling. So you can say, here's my net of concern. Go and tell me all of the coupling capacitors that couple to this net and sort them by the highest to lowest. And then also, once you identify that, you can see it over here, identify this thing, graphically represent it. You can pop up and actually identify what layers those are on. It's hard to see here, but that's metal 2, and over here it's metal 2. And so you can identify what that coupling cap is on that net that has the highest coupling caps. The thing is differential pair analysis. So if you have a highly sensitive circuit and you want to do differential pair analysis, we can do that as well. You can see that contact 3 lines up pretty well, but contact 2 is a little bit off. So that will give you a hint of an area where you might want to go and look at your net and figure out where this contact 2 is not off, or metal 2 as well. Another feature in the tool is what if analysis. You look at your design, you see a problem, and you can say, well, if I added 4 more vias or changed metal layers in this area, what would it look like? And you can type it in, say I want to add vias here, I want to do that, and then you do another analysis and you can catch that before you have to go modify your layout. So the whole idea here is to catch everything before you go to your simulations and not waste a lengthy simulation runtime. As I hinted to a little bit earlier, you're actually able to connect the Viso GUI with Virtuoso. So you can actually see real layout. You can actually bring the GDS into the Viso GUI, or you can, like I said, connect it to Virtuoso. So when you zoom in on this net, it'll zoom in on your Virtuoso window. So you can identify the problems on real layout, get the real details. And some of the highlights and some updates, we're now doing equivalent pin-to-pin resistance across devices, not just nets. We have a lot of sanity checking, 2.5 speed up, 2.5x speed up. We're always working on the tools, trying to make them better. So this is just some of the things that we've added in recently. And so what does Viso do for you? It accelerates your parasitic analysis and optimization and debugging cycles. It allows you to identify problems before simulations. Thank you.